Hi, lecture 4 this week means we get to put this into practice. Development of a dynamic model for distillation. So a lot of the things we've been talking about this week, you can see the immediate practical implementation and benefit of it. So we're going to follow the lecture notes for a little bit on this one. What do we need to do? First 4 steps. Identify the input and output variables. So this is talking about a real problem where it's not been presented to you on a plate. You need to take a look at it and have a think about it. What's the inputs? What are the outputs? And then you need to take an input and introduce a step change. So this is about finding out in a systematic way how an actual system behaves. So when I say development of a dynamic model, this isn't about solving it all with equations and working out exactly how every part of it's going to behave. It's about taking a real process and putting a model to it. So thirdly, once you've introduced your input variable and made a step change, you select an output variable and trace its response. See what actually happens. And what we have now are the tools so that we can develop the first order model with a delay appropriate and approximate to the response. So we've seen that that's a valid and a reasonable way of detailing that response. And we've seen now a way of combining these together to give a complete model for the process, for a process with multiple inputs and multiple outputs. So our example is distillation. Here's a distillation column, has a feed coming in. Of course, you've got a top product coming out, which then gets condensed, and there's a reflux coming back into the column, and now our top product of composition XD. Likewise, at the bottom, comes out as a liquid. A reboiler puts vapor flow rate back in, and then bottom product is XB. We're going to say our feed is fixed in this case, but we have a choice of reflux ratio and the amount of vapor boil up V that we do. Our outputs, what are they? Well, XD and XB are the outputs, the compositions of the top and bottom product. So we can draw that as our simple model now. R and V are the inputs, XD and XB are the outputs, and distillation is the process we want to model. Obviously, you know about McCabe-Thiele methods and all of that, and there's a whole lot of things that will go on in here. The beauty of this is that from a control point of view, we can simplify all of that into a very simple model. So our feed is a fixed input. So to address this problem, well, we need either an experimental device, so something we can experiment on. It might be a model of the actual process that you can do experiments on. Maybe you've got the opportunity to do trials on a real industrial process. Or perhaps you have a simulation model, so something in HYSYS which is simulating the actual process, and that enables you to develop some synthetic results that you can use to develop a control strategy. So we said we want to input a step change to one of the inputs. So let's choose the reflux ratio R, and we'll keep V constant whilst we do this. And we introduce a unit step change into the reflux at some time. And we look at what happens to our outputs. Let's look at XD and see what happens. Okay, so you've plotted some data here as XD changes with time, and we've seen from the previous mini lecture that we would expect this to be slow to begin with, some delays, and then it would tend to then approximate a first order response after a little while. And we saw that we can simplify this by extrapolating down at this point of inflection here, extrapolate back at constant gradient to the XD equals 0 line, and then we can treat this first period as simply a delay in the response, and the second period we can treat simply as a first order response. And remember that we could find the values for the first order response constants. K is the value of XD as it tends to steady state, and then we can find tau, the time constant, by finding 63% of the way to XD and coming down and finding the time difference between the delay and that point. So we can then do that. We can extract that information very readily from either experimental data or simulation data and come up with our transfer function. So we have two parts to that. This first part is the first order response, and then the second part is the delay. So that's one transfer function which represents one combination of input and output. Of course, we've got 2 inputs and 2 outputs, so there are 4 combinations in total. So we can also see how does the distillate composition change with a step change in vapor boil up. How does the bottom product change with a step change in reflux ratio, and how does the bottom product change with a step change in vapor boil up. So you can repeat your experiment, each time keeping the other variable, the other input constant, introduce a step change, and then look at the appropriate response, and then come up with an approximate model for each of those. So we have 4 transfer functions to describe our system. And of course this can be written in matrix notation. So our outputs equals the transfer function times R, transfer function times V, add those together. We can do that because the Laplace transform is a linear process, so we can just add up the 2 responses to get the total response, and likewise for XB. So that illustrates how simple it can be to take a complex process and then turn it into a manageable control problem. So this approximate model that we've used, it hides the higher order dynamics. We know that there will be higher order dynamics in a process like this, but we know that those higher order dynamics always tend to create a lag effect and something that looks a bit like a first one. The overdamped response is the most common case, but not the only one. So we've seen how to apply this now, a dynamic model to a real process, which is excellent and very useful, and you'll do that in your problems. The final note is about linearisation. So the Laplace transform method only works for linear equations, and we've always emphasised that we need, we've been looking at first order or second order linear ODEs, and the word linear is important, and it tells us that our variable, in this case our principal variable x, needs to only have powers of 1. So if we have an equation, this is the first order ordinary differential equation, but if this is a non-linear expression of x, if it's like x squared or sine x or anything else like that, it's non-linear, and the Laplace transform method won't work, and also the deviation variable method won't work. So we need to linearize this in order to apply our methods to it. So that's no problem, because we have a method from that from first year. We've got the Taylor series. So the Taylor series will approximate a function f of x by finding a succession of terms which approximate it. So it works very nicely, but it has the limitation that it only finds the approximation in a local area around a particular point. But that's okay for us, because we're particularly interested in the local area around the initial steady state. So we're going to take the point XSS as the point of interest, and the Taylor series approximation then is equal to fxss plus the partial derivative of f at xss multiplied by x minus xss plus all of the other higher order terms, which we will neglect in our simple approximation. And when we use deviation variables, of course our function at xss will be equal to 0. So that term disappears as well. So we rewrite that. Our equation can now be expressed as dx by dt is equal to df of x at dt at xss multiplied by x minus xss. Substitute in for x in terms of the deviation variable, and now we can rewrite the equation, whereas x dash is the deviation variable, dx dash by dt is equal to a x dash, and a is equal to the partial derivative of f by x at the point xss. So that's a simple linearisation and an approach that we can employ for cases which are non-linear in the first place. In the lecture notes there's a further example which you can work through on your own and consult as you do the problems, and then that will conclude our lectures for week 4. Lectures for week 3. Good luck with the problems, and we'll see you in the class.